A spreader is traveling across a farm field in Los Banos, in California's Central Valley. This cropland is owned by Bowles Farming Company. Derek Azevedo is its vice president.
This land has been under the stewardship of the same family for 160 years, and our charge is trying to figure out how to maintain its productivity and maintain its health and improve on all those things for the next 160.
Which is why they're working with UC Davis researchers to take part in one of the largest experiments of its kind. It starts with this spreader. It's applying rock dust to the soil. Climate scientist Ben Holton, an affiliate faculty member at UC Davis, says rock dust has the potential to store carbon, and lots of it.
There's estimates that we could get 4 billion tons of carbon dioxide removed from the air each year if you put these kinds of rocks on our global croplands, which is about 11% of Earth's surface.
Agriculture has a huge carbon footprint, but done right, it could be one of the world's biggest solutions to climate change.
Climate models all agree that temperatures are going to increase.
It's going to be hotter, it's going to be drier, fire's going to burn more frequently.
Maybe this is never going to be the way it was again.
We need to come up with ways to literally pull CO2 out of the atmosphere.
How are we going to work together to solve a challenge like climate change?
Coming to you from our closet studios as we shelter in place across the Sacramento region, this is Unfold, a UC Davis podcast that breaks down complicated problems and discusses solutions. This week, we unfold rock dust. I'm Amy Quinton.
And I'm Kat Curlin.
Last season's Unfold discussed how to sustainably feed a growing population. It's a task made much more difficult by climate change.
Last year, the Intergovernmental Panel on Climate Change, the IPCC, came out with this major report that looked at agriculture, forestry, and other land changes. It found nearly a quarter of our global greenhouse gases come from these sources.
That's right. The report said it will be difficult to prevent temperatures from rising above 2 degrees Celsius without fundamentally altering the way the world produces food and uses land.
Agricultural greenhouse gases come from different sources. Cattle belch methane, which is a potent greenhouse gas, and fertilizers that help grow our food release nitrous oxide.
A study by UC Davis researchers found in California, agricultural soils can release up to 41% of all of our nitrous oxide emissions. That said, Ben Holton, who we just heard from a moment ago, says agriculture can also be a weapon in the fight against climate change.
I don't think there's any industry on the planet that is more positioned to create negative carbon emissions. That means there's more carbon dioxide being taken up by the systems and being emitted than agriculture.
Kat, he says it starts with the soil. Every time a farmer churns up or tills soil to grow food, not only can soil lose critical microbes that make it healthy, but carbon dioxide is also released into the air.
So that begs the question, if farmers keep their soil healthy, could they also keep carbon in the ground instead of the atmosphere?
We know it helps. Practices like no-till farming or adding things to the soil like compost can restore soil health. And it's that last practice of using so-called soil amendments that UC Davis scientists are researching.
Okay, compost is one thing, but rock dust? In this episode of Unfold, we're going to look at adding rock dust to croplands to see just how much carbon it can capture.
These farming practices that can improve the rate at which carbon dioxide is removed from the atmosphere is often called carbon farming. So, Kat, you might think we'd start this episode on a farm.
But I guess I'd be dead wrong to think that a story on carbon farming would start on a farm.
Yep, we have to start at the source, where we get the rock dust that's going to be added to the farm.
And where was that?
A mine in Ione, California, which is up in the foothills of Amador County. And coincidentally, that's near Carbondale, which is appropriate for this story, right? Carbon farming, Carbondale, get it? Okay. Okay, ready for this? Listen.
Should I guess what this is besides a bunch of noise?
This is the sound of rocks on a conveyor belt at Specialty Granules. The company mines this rock out of an open pit quarry.
And why are they mining rock?
Well, mainly the rock is crushed into small pieces and sold to roofing companies to make shingles and other roofing materials. The rock in this case is metabasalt.
Metabasalt?
Metabasalt. It's a fun word to say. So George Diaz, he's the site manager at the mine. He drove us up to the top of a hill where you can get a bird's eye view of all the activity at the mine. And he explained how these rocks are crushed.
So those are boulders that they're bringing up and gets through a primary crusher, a jaw crusher that brings that rock down to about a 9.5-inch rock.
That's industry speak for the size of the rock.
So it's 2 closed loop circuits that continue to crush and screen until we get our 7/8-inch minus material out the back.
It's then milled into smaller sizes to use in roofing materials. But there is a byproduct of all this crushing, which George drives us to see.
This is dust.
He points to several towering piles of gray material. He says some of it, the coarser material, is used in horse arenas. But most of it, this fine dust, is useless, a waste product, and ends up in a landfill. Ben Holton says while it may be the wrong size for roofing materials,
It's just the right size to add back to soil, to rejuvenate the soil, grow our soils, and do it in a way that starts to provide major benefits for the crops that we're trying to grow. And in fact, previous studies have shown that you can increase crop yields by 50% adding these rocks back to the soil.
Amy, 50% is a lot. How does that work?
50% is, of course, the high end of what it could yield. It turns out that this is a pretty special type of rock.
So this rock is the kind of rock that produces some of the most nutrient-rich soils on the planet. It comes from volcanoes, and then this particular kind, it's very enriched in silica and vital nutrients for plants, especially potassium, which a lot of our growers need.
So a little bit of science here. Silica helps plants form thicker cell walls. Ben says it prevents lodging, and lodging is when the stems of plants, like wheat or grain, bend over near the ground.
So that would make the plants difficult to harvest.
Right, so thick cell walls and nutrients, good for plants and yields.
Okay, so how do these rocks store carbon?
We'll unfold that complexity in a bit. In a nutshell, though, as these metabasalt rocks, which are highly pulverized, as they weather and dissolve, they consume carbon dioxide from the air.
We're going to see how much of the CO2 that is dissolving the rocks goes into a form in the soil that sticks around for a long time.
So researchers want to know this.
Can you accelerate that reaction to help us drive negative carbon emissions in a way that helps grow food more efficiently, given that we're going to be at 10 billion people by 2050, and we have to find a way to simultaneously grab 10 billion tons of CO2 from the air each year to meet the needs of the climate targets for the Paris Agreement.
By the way, since 2015, scientists have used the Paris Agreement as a reference point for climate change targets.
Ben said in the beginning of the episode that, at least theoretically, we could remove 4 billion tons of CO2 each year by adding rock dust, right?
If it were spread across all of our global croplands. Right now, researchers are trying this out here in California, adding rock dust to 30 acres of different crop soils in Yolo County, the San Joaquin Valley, and in the Imperial Valley of California.
That's still a big experiment.
I caught up with the farmers and researchers in Los Banos in the San Joaquin Valley.
Yeah, the big pile. 18.3, what's that? 9.15.
UC Davis researchers unreel a tape measure on a 6-acre field owned by Bowles Farming Company. Organic corn or tomatoes are typically grown here. Iris Holzer, a PhD student, is measuring out large uniform plots or blocks on the field that will be part of the experiment.
And in each block, half the block is getting rock, half the block is a control.
Iris is a woman who is downright passionate about soil. She explains how adding rock dust to this field can capture carbon.
When the rock weathers and reacts with CO2, there are two different forms that the carbon can be stored as.
And not to get too in the weeds here, but the carbon can form either carbonate or bicarbonate. If it's carbonate, then carbon will stay in the soil a long time, thousands of years or more. Iris says that has significant upsides. Researchers are happy with what they found in the soil so far.
And the soils are very exciting.
Well, we found carbonate.
Yeah.
You know, to explore and find little carbonate nodules, there's nothing like it on the planet.
Awesome. Very
It's like
exciting.
discovering diamonds.
Yeah.
But no, I mean, I think that tells us that the capacity for mineral formation will be good, and so that we imagine there'll be good carbon sequestration capacity when we apply the rock.
Several piles of rock dust, about 6 feet tall, line the farm field. A loader begins to shovel the piles into a spreader. As the spreader travels down the field, it spits out a light greenish-gray coating of rock dust. Maya Alvarez, a biogeochemist in Ben's lab, has been working on this project for 2 years.
It's very exciting to finally see it go out. There's been a lot of planning and scrambling to get it done in a somewhat short amount of time. And so it's really cool also to see it at such a large scale. So usually when we set up plots, they'll be maybe like 20 by 30 meters. And this is, a whole acre being spread with a certain addition.
Scientists are applying 16 tons of rock dust per acre. First, it will be applied to this organic cornfield. Ben Holden says they'll then apply it to the soil of conventional alfalfa.
We're kind of trying to figure out, when you go from an organic to conventional, are there distinct differences? And then when you go across globally important crops that are important to California, are there any differences as well? Ultimately, we're hoping that these technologies can scale outside the state, so working on corn and alfalfa makes a lot of sense if you want to create demonstrations that have meaningful impact.
Alfalfa also has some of the highest nitrous oxide emissions in the world. This work is part of a much larger multi-campus collaborative effort researching carbon sequestration using other soil amendments, including biochar and compost. Maya Alvarez says these large-scale demonstration projects hold huge potential.
The only way to make these climate solutions be highly adoptable is to create these win-win situations where they have to be economical, they have to increase yields, they have to be fairly easy for farmers to do, and they have to have good science behind them that is verified.
Those are some of the reasons Bowles Farming Company is taking part in this experiment. Vice President Derek Azevedo says he wants to improve this soil to help his crops, but it can be hard to know what works the best.
One of the challenges with soil amendments and soil health is that 90% of the people out there marketing and providing the information as it relates to soil health are people that are trying to sell you something. And so really sorting through, here's something that's valuable versus here's somebody who's just trying to sell me something, another charlatan, is difficult.
Derek says this demonstration comes with little risk. The rock dust was donated. The farm, like a lot of farms, already has a spreader, so they didn't need any special equipment. And then there's the potential to increase yields on an organic crop.
And if we have the opportunity to help sequester more carbon at the same time as improving our soil health and potential crop yields, I mean, those are all very, very useful and very powerful metrics that can create something that can sustain itself and build off itself. I mean, that's what we're here for. I mean, agriculture is a large industry, and harnessed in the right way is one of the few industries that is big enough to make a difference.
Researchers are measuring both carbon dioxide and greenhouse gases like nitrous oxide coming off the land. They'll be looking at how much water is stored in the soil after adding rock dust, and they'll be looking at what it could all mean for farmers' bottom line.
Amy, if we did this all across California croplands, what effect could it have on our carbon footprint?
I asked Ben Holden that very question.
We did calculate that if you took some of these kinds of rocks and put them at a moderate level on California's croplands, we could get anywhere between 30 to 80 million metric tons of carbon dioxide capture each year. Right now, states' emissions are somewhere around 440 million metric tons. That is a very big number that we could get. And ultimately, I think that is where the potential lies.
So, Amy, would this be easy for farmers to adopt, especially worldwide? Is there even enough rock dust?
Ben says there is enough rock dust in California. Some studies have shown that there is enough worldwide, but those same studies have also shown that it could get expensive and may not be worth it for the farmers.
So, do we have results?
We have preliminary field results from here at UC Davis that showed a 30% increase in yields of organic corn by applying this type of rock dust to the soil. They saw a 12% increase in yields in conventionally grown corn. Scientists are still measuring greenhouse gases and yields on this large demonstration project, and they hope to have answers soon.
And we'll let people know as soon as we find out. You can also visit our Unfold website to find out more at ucdavis.edu/unfold.
I'm Amy Quinton.
I'm Kat Curlin.
Thanks for listening. Unfold is a production of UC Davis. It's produced by Cody Drabble. Original music for Unfold comes from UC Davis alumnus Damian Verrett and Curtis Jerome Haynes.